All right. Hello, astronomy. Today I'm going to be covering the chapter Starbirth. It's actually a short chapter, basically 3 sections. We're going to talk about stellar nurseries, stages of starbirths, and then masses of newborn stars. So, kind of a short chapter. But where do stars come from? They come from stellar nurseries, basically star forming clouds that have a lot of dusty gas in them, and we call this an interstellar medium. The composition of these clouds tend to be mostly hydrogen, then followed by helium, and then some heavier elements, and especially in our region of the Milky Way. In other regions of the universe, the percentages can be a little bit different, but we know this by studying the absorption lines of these stars. They can also be a part of molecular clouds. So most of the matter in star-forming clouds is in the form of molecules, not just helium and hydrogen. A lot of times we see hydrogen gas, H2. I think it's supposed to, some water, H2O, CO, carbon monoxide, etc. So these molecular clouds tend to have very low temperatures, 10 to 30 Kelvin, density about 300 molecules per cubic centimeter. And mostly what we know is by studying emission lines of carbon monoxide. You might also find some interstellar dust in these clouds, particles less than a micrometer in size, made of elements like carbon, oxygen, silicon, and iron, so heavier materials. A lot of times when you view stars through the edges of these clouds, they may appear redder, as you can kind of see in this picture right here, due to the dust blocking the shorter wavelengths, blue light than red light. So we call this interstellar reddening, where long wavelength infrared light passes through a cloud more easily than visible light, so we get to see infrared light on the other side of this cloud. Now, observing newborn stars, a lot of times we can see the visible light, but it can be trapped within dark, dusty clouds where the star formed, and we can also observe infrared light, which can reveal a star that's being born or embedded in it. Okay, so here are some examples of nebulas. I think this is called the eagle pillar. I'm blanking on the name. My daughter's distracting me. Visible light image shows immense pillars of dark molecular gas, and they can be sculpted by ultraviolet radiation. So yeah, different. These are the same images, just as shown in infrared. So yeah. Okay, some dust grains can also glow. They can absorb visible light and heat up and emit infrared light, so we can detect those in the night sky. So it says long wavelength infrared light is brightest from regions where many stars are currently forming. So these are glowing dust grains. Now, why do stars form? Well, in our previous lecture, we talked a little bit about gravity and pressure, how they're trying to find this balance between the two. But gravity can create stars only if it can overcome thermal pressure in a cloud. And so the mass of a star forming cloud, it's a huge factor. How much mass does the star have? So it has to contain at least a few hundred solar masses for gravity to overcome the pressure. And again, we know this from emission lines. So the resistance to gravity cloud must have even more mass to begin contracting if there are additional forces opposing gravity. Both magnetic fields and turbulent gas motions increase resistance to gravity. So now I'm going to talk about the fragmentation of a cloud and kind of go through the stages here. So gravity within this contracting gas becomes stronger as it becomes denser, and then once it overcomes pressure, it causes it to break apart, and this is where it's called fragmentation. Each may go on to form its own star. So this is just a simulation picture. This is not a real picture of a cloud going through fragmentation. But then we have random motion of different sections of the cloud that cause it to become lumpy, and each lump again could become a star. So a large cloud can make a whole cluster of stars, and we talked about there are 2 types of star clusters in a previous lecture. Sometimes stars can form in isolation, where only a single star can be made, kind of like in our solar system. But the first stars, were mostly made of different stuff than they are today, because carbon and oxygen had not been made yet, through supernovae, which I'm going to discuss. So without carbon dioxide molecules to provide cooling, clouds that were formed the first stars were probably warmer than today's molecular clouds. So simulation of the first star suggests that they never cooled below 100 Kelvin, and they made stars that were a lot massive then than they are today. Think about 100 suns. Moving on to the second section, stages of star birth. So what slows the contraction of a star-forming cloud? Basically, what slows it has to do with how packed the molecules are, and then thermal energy is going to build up because it's being packed, and as you increase your thermal energy, your internal pressure is going to increase, and then as a result, contraction will slow down, and you'll get something called a protostar, which is not quite a star yet, but it's a cloud fragment that becomes like the pre-stages of a star. So matter falls into the center of the protostar, or maybe matter just around it blows its surrounding way. Whoa. So rotation also plays a factor in star birth. We talked about rotation of galaxies and how they form. So the Nebula Theory illustrates the importance of rotation. We talked about the conservation of angular momentum, that as matter falls towards the center, it starts to spin faster and faster and faster and can flatten into a disk. And as it flattens into a disk, we have more collisions, which randomly reduce the random motions of molecules. Collisions between gas particles also, again, reduce up and slow down the motions. Eventually, like I said, it's going to flatten and shrink. And then sometimes it can cause jets of matter to shoot out on opposite ends. So nuclear fusion is the start of a star. So when we go from protostar to a star in the main sequence, nuclear fusion has begun. So if it's star-like and the surrounding gas is blown away, its thermal energy comes from that gravitational contraction, not fusion. But then once fusion starts, now it is a star. Birth stages. So we've seen the HR diagram and we've kind of done some work with it, but it does illustrate a star's surface temperature and luminosity at different moments in time. And luminosity and temperature grow as matter collects in a protostar, and it can start here and just move on down, or maybe it starts here and it moves on down. But the thing I just want to emphasize is like it can leave the main sequence and become a red giant at any time, basically. So the life tracks of different masses of stars is different, where as you can see that the bigger mass of stars tend to have shorter lifespans compared to stars that have smaller mass. So high mass stars form faster, low mass stars form more slowly. And then that also affects their lifespan as well. So the masses of newborn stars, what's the smallest mass a newborn star can have? Where did I list it? I think I listed it on the next slide. So like I said, fusion, you have to have fusion occur. And, sorry. Larissa, can you please leave? Go to Dad, okay? Thank you. All right, so thermal pressure cannot stop contraction because the star is constantly losing thermal energy through radiation. So is there another form of pressure that can stop contraction? Yes, there's actually two. Degeneracy pressure, which we've talked about in chemistry. Two electrons cannot occupy the same state in the same place, or basically the same spin. And the other type is thermal pressure, which depends on its heat content. Brown dwarfs are basically failed stars, so degeneracy pressure halts the contraction of these objects if the mass of it is less than 0.08 of our sun. Star-like objects are not massive enough to start fusion are considered brown dwarfs. Basically, they don't have enough mass to undergo fusion. So it does emit infrared light. They're a little bit harder to see, and its luminosity will gradually decline as it loses its thermal energy. What's the greatest mass that a star can have? 150 suns. That's the maximum, but new observations could indicate it could be larger. So stars with any more massive than 150 would basically blow apart. Anything less than that can't sustain fusion, so you get the brown dwarfs. Now the typical mass of newborn stars tend to be on the smaller side. So star clusters tend to show low mass. There are more low mass stars than high mass stars. Okay, sorry, that was, I got distracted several times from my daughter, but there's chapter 16, Star Birth. Tomorrow we'll talk a little bit about chapter 17, looking at stellar, or basically star stuff.